All right, reaction video number 49, which is a great number, if you ask me. 7 times 7, wonderful, perfect square. It's also my birthday, 7/7, so there you go. So today, what did I do a search for? I think I did honors physics this week or something like honors physics and then filtered by this week. And I found this, so away we go. Let me just do that. All right.
Hello everybody, Mr. Hinnon here, and as you can see, I'm in the classroom. I even have, if you kind of look over here, you can kind of see some plans for Physics 1, some plans for Physics 2 over there, and we're kind of ready to start. So these notes are going to be over Chapter 19, and I want you to kind of work on them after you've kind of finished up all the stuff on Chapter 18. We're going to end up having a Chapter 18-19 test because that's going to be all kind of clumped together. But this one's going to introduce two major things. It's going to introduce the idea of potential energy and potential. They are actually different. And one of the first things I think is good to kind of start off with is this idea. Let's relate this to gravitational potential energy. If I have a basketball sitting up here in the air, and I am looking at it, we know that this basketball has a certain amount of gravitational potential energy at a certain point. And then if I let the basketball fall, its gravitational potential energy is going to decrease. So it's going to go to a lower value here. And basically what's going to happen is work is going to be done by the gravitational field to move it from high potential to low potential, high potential energy to low potential.
So just going to pause here. So I've taught this stuff a ton, and the major issue is the signs. And so yeah, when you start with gravitational stuff, mostly the students are going to be nodding along, like yep. We go up, you go down. Yep. Gravitational potential energy has been drilled pretty hard for most students, and they sort of get it, right? So you heard him say some really, really interesting things. He said you have it up here, and if you let it fall, it's going to go down, and its potential energy is going to decrease. And of course, there's if you were doing, your energy accounting, right? You say, oh, well, yeah, it's going faster and faster. Oh, well, if it's going faster, its kinetic energy is going up. Oh, well, that must be at the expense of gravitational potential energy. So I think that this analogy is going to work great when he comes over here to the electric stuff going on, especially when you think about the work being done, is it going where it wants to go, all of that stuff. But all of a sudden we have the sign problem in electrostatics, right? That charges can have a negative sign. And so electric potential energy and then potential just get students just totally twisted around. And so I think that he's starting with his really great analogy that doesn't have that problem, right? We don't really have negative mass. So we don't ever have this thing where all of a sudden some balls go up and other balls go down. So certainly starting here and reminding students of what they know, and hey, this is all pretty straightforward stuff, hitting all of the major pieces, he's going to be able to use that analogy moving forward.
Low potential energy. Well, the same thing would happen if I had some kind of charge. Let's assume this is a positive charge, because we usually always do our test charges as positive. Q0, and I put it at this point right here, and then I let it go. What would it do? It would tend to want to move toward this negative plate down here, and so we would say that its electric potential energy is going to decrease, and basically work is going to be done by the electric field to do that. And so we could calculate that change in electric potential energy. Here's the cool part. If you write it like this, the charge times the electric field times the distance it is away from the source of the electric field, that is a way of finding the electric potential energy, just like mass times gravity, which is actually like a gravitational field. It's newtons per kilogram times a height or a distance away from whatever's creating it. Now, in this particular case, it would be a little bit difficult because you actually have two things that are producing this, but they're going to produce an electric field that would point in this direction. It would go from the positive, and so you would probably measure from the bottom up to those particular points.
So I just want to back him up a little bit. Lots of really cool things there, and subtleties, right? So when he first started talking about putting a positive charge here and saying it would go down, he didn't say it would go down because the field is pointed down. He only said that later. He said it would go down because there's all these negative charges down here. Like, oh my gosh, that's where I want to be. So if we can help our students understand that electric field, it points away from positive charges and towards negative charges. And that's kind of a convention, but, damn you, Ben Franklin. But if you go to the things that they're never going to forget, like opposites attract, that's something that, man, it's just, they just know that stuff. And so the positive charges is going to want to go down towards these negative charges here, and wants to run away from these other positive charges. So if you already know the direction it's going, and if you let go of it and it achieves some kinetic energy, it must have given up some electric potential energy, which is what he's talking about here. I also really, really love the direct analogy, right? Three things. And to do it that way helps you realize, we never really do it with gravity. We never just say GH is this thing, but we're going to say that E times DA is a thing here in a second, right? That's what electric potential is going to be. Then to say, okay, and you just have to remember that the field points away from positive charges and towards negative charges, then it's all going to hold together. But man, it is really subtle, and it just gets worse when we start dealing with electrons here in a little bit.
And so you would probably measure from the bottom up to those particular points. The other one is electric potential. So electric potential is really just defined as the electric potential energy divided by the charge. So it's kind of like electric field is to electric force. Mm-hmm. Electric potential is to potential energy. It takes away that test charge. And so when we talk about electric potential, we talk about it being in joules per coulomb. This should actually be a capital J, sorry. And a joule per coulomb is the same thing as a volt.
So there's this moment, right, when the students are like, why the heck are we doing this? I hated it when we went from force to electric field. I hated it because force made sense to me. Like, I just need to think about which way it wants to be pushed. And then you had me start thinking about electric fields as this divide by the test charge business, right? So I've just seen it in the faces of students. And they're just like, and if I can take a homework problem where I'm working with them one-on-one in my office, and I'll say, okay, well, what do you think this charge wants to do? And they'll say, well, what's this charge? I say, let's make it a positive charge. Oh, well, it hates other positive charges, so it would go this way. I'm like, sweet. So, what direction is the electric field? And they'll be like, well, hang on. So the force is, so they want to think about what sort of the feelings that these anthropomorphized charges have. So they go force to electric field only because I asked them to. Right? Only because the problem asks them to. And similarly for potential energy, they're like, oh yeah, it's just like gravity. I'm good. Oh, I got to divide it by the test charge again. So all of this is happening, right? All of this confusion is happening, or this feeling like, why do I have to do all of this stuff? Why do I have to move away from the things that I think these charges would feel? And then there's this moment when you introduce this unit, and it's the first time in a long time that they're hearing a unit that they've heard of before, right? So joules, they learned first in a physics class. Coulombs, they learned first in a physics class. All the stuff with electric fields, charges, all of that stuff is new. And then they land here. And they're like, oh, I've heard of that. Volts. Oh, like a 9-volt battery. Oh, like the 12-volt battery in my car. Oh, volts. And that's when you, as a teacher, we have to pause and say, oh, yeah, you do care about this. Oh, this is totally realistic in your life. So, oh, man, we have to pay attention to this. I thought it was just going to be this thing that I had to do homework on and do it only because you asked me to. But it's like this moment where we say, I've been leading you down a path. I've been hoping for you to explore this path with me. And suddenly we're to something that actually matters. And you'll know this in situations in the lab, in real life. So all of a sudden, this definition matters a whole lot more. So I just think I really loved how he did it. He walked us through and we got here. And then, of course, there's always this problem of students thinking, well, but in physics classes, things don't mean what I used to think they meant. What's a good example? Work, right? So work it makes you tired in real life, but holding out something, just holding it here, I'm not doing any work, so I can't get tired. Oh, but I do get tired. Oh, so physics work is not real work, right? maybe that's true of this volt thing, right? Like, oh, maybe that's not like battery volts, right? So I just think it's such an interesting moment when we're teaching this stuff.
Capital J, sorry. And a joule per coulomb is the same thing as a volt. So when we talk about voltage, we're actually talking about how many joules per coulomb this test charge has. So again, as you move between these two different points, you're going to have a difference in electric potential. Now, here's one of the key ideas. Notice that they write the difference between B and A. So as you start at A and then move down to B, what is the potential difference between those points? It's the difference between the energies, but B was at a lower energy than A was. And so because of that,
Confusing.
you can actually get a difference in voltage or a difference in potential. V is actually going to be used for potential. And in this case, it would be the opposite of your work per
So
unit
hard.
charge. So in other words, the change in electric potential energy, we have the field do work to move it that way, but we're actually going to be talking about the more energy you have, the more potential you have. So
I just want to pause and just like applaud this, right? Like everything he's saying is exactly dead on right, but it is so hard. It's like, why are we working so hard to add all of these extra negative signs? It reminds me so often in a class where we're working on a problem that's basically multiplicative, right? So take a look at all of these equations we're looking at here. They're finding differences of things, but each individual term is completely multiplicative, right? And so I'll say, okay, look, you guys, this whole thing, this whole term is either going to be positive or negative. Let's just drop all the negative signs and let's just figure out the magnitude. And then let's just ask ourselves, should that have gotten bigger or smaller? Is that a positive thing or a negative thing? Right? And trust your instincts. Well, all of a sudden now we're just throwing negative signs at them like crazy, right? And so you'll have problems that have like 4 negative signs in it. And so I think obviously the next thing to do, exactly as he's doing here, is an example. So really, really tough. And I think it's hard to motivate, frankly. Luckily, there's that unit, like volts. Oh, volts. Oh, okay, volts. Let's see if we can do some cool stuff with volts. All right, let's keep going.
Here, let's try a little sample problem. Let's say that you have a positive 2 microcoulombs here, and it's at position A. Whoops. And you're going to let it move. Sorry, the thing doesn't always register my pin when I do it. And it's going to move from point A to point B here. And that is going to have the electric force, the electric field is going to do 5 times 10 to the minus 5 joules of energy moving that. So the difference in potential energy between these points is pretty easy. And then the electric potential difference is going to be the same idea. So the change in potential energy is just going to be the difference between those energy points, but we often talk about it being negative. So it's decreasing as it goes from A to B, it's actually decreasing that energy. So that 5 times 10 to the minus 5 joules is going to decrease because this is at lower energy than this is. That also will allow us to figure out what is the potential difference between these. So we talk about the difference in potential, and it would be negative 25 volts. This is
so that's another reason that potential is so much more interesting, because the numbers are just these nice, manageable not integer, but macroscopic numbers. So if you're sick and tired of doing all of these times 10 to those, right, all of these super itsy bitsy numbers, whether it's we're talking about charge or whatever, typically our volts are going to be nice round numbers, because almost everything we do in the lab is going to be, between 1 and 100 volts. Right. And so it's kind of nice that all these times 10 to those kind of go away when we talk about voltage. Man, what a great example. It's obviously the same image that he used originally. Again, students are like, oh yeah, of course it's going to go down. It's going to be going faster, so it's going to lose potential energy. And okay, well, you told me to divide by Q. Fine, I get negative 25 volts, but I don't think the students really care yet, right? But if you were to think of that, you would achieve this by hooking this up to a battery. It would mean this would be from here to here anyway, would be a 25 volt battery. This must be this must be like maybe a 30 or 40 volt battery, making this in the first place. So we're not talking about that yet.
This is basically because we tend to think of, when you think of the voltage across something. So if I connected this to some kind of voltage, we would say this is at, say, a positive, let's say 200 volts. And we often say negative is at 0 volts. And so when we're talking about this, if I go from positive toward the negative, I am decreasing my voltage. So I'm going from 200 down to 0. If I went from 0, I could increase the voltage up to the positive. So again, we're always thinking of the way positive charges are moving, which is kind of weird. And that's what this is talking about. If I were to put a positive charge right here at point C, it would move from this lower potential toward the higher potential. So it would move from C to A if it was a positive charge. And we often talk about positive charges. If it was a negative.
All right, so I think he made a mistake there, but let's just double check. And very likely he's going to fix it here in a second if he did make a mistake. So, and of course, you know that I'm so excited to watch people sort of think critically on their feet. So first, let's talk about that. I need to rethink think if he actually made a mistake. He might not have. It may have been me, but right. So I can't quite see. Let me if I move my thing. So we're 6 minutes into his video, right? And let's say you make a mistake 6 minutes in. What do? Well, you have 3 options. Stop and start again. Then you have to erase all your marks, right? Keep on going, but know that you're going to do some post-production, okay? So I personally never, ever do post-production because I just want to move forward. And number 3, hopefully catch it, right? And fix it right now. So what I think I heard him say is that if you start a positive charge at lower potential, it will naturally gravitate towards higher potential. Is that what it says? Positive charge accelerates from a region of high potential. Okay, so this is the opposite of what he said. And the negative charge accelerates from low. Okay, this is a picture of what a negative charge did. So I have a suspicion that he's going to fix it. He might not, right? I don't know. I haven't looked ahead. He might not. Let's say he doesn't. For sure, in his examples, he's going to get right? Because the examples, are much more structured than this little cartoon. And how do you deal with it? Well, the student might say, boy, I was super confused. But what you said didn't make any sense to me. And, as an instructor, you might say, no, look here. This is exactly what I said. And the student's going to say, boy, I don't think that's what you said, right? And that's that moment in your office or in class. It's like, oh, shoot. Yeah, gosh, I did say it wrong. You know what I mean? And so I think that there's to foster a learning environment where students are okay to sort of call your bluff and say, what? Huh? I'm confused. It's interesting. This is not live. The students aren't going to do it immediately. So if he doesn't catch his there's 4 things that are going to happen. 1, he's going to catch his mistake as soon as I unpause. 2, he's going to catch his mistake when he gets to the examples and say, oh wait, hang on a second. Is that what I said? 3, the students are going to catch it and ask him the next day. 4, no one's ever going to catch it. And how much damage does that do? And frankly, I don't think much here because if we've got a good 10 minutes left in this video, I'm not going to watch the whole thing. It's going to get fixed. So I'm just going to back it up and let's see how it goes. Well, maybe a little bit further. Let's go.
Positive charge right here at point C, it would move from this lower potential toward the higher potential. So it would move from C to A if it was a positive charge. And we often talk about positive charges. If it was a negative charge, it would actually be moving the opposite way. It goes from a higher potential to lower potential. That's why we typically use positive test charges because they make more sense. They follow our kind of general idea. Water, fluids flow from high pressure to low pressure. Heat flows from high temperature to low temperature. Positive charge should flow from high potential to low potential. But in this particular case, we talk about kind of the difference. And so this one's kind of a weird one that we want to actually have our charges moving in a particular direction. So this is kind of, if we talk about this positive charge, this is where the positive charges would want to end up. And if we switch this out for a negative, if this was a negative charge, it would tend to go up. So we end up with negative charges up here. And so we get them moving.
Okay, so he fixed it, right? And did you watch his face? I actually think it registered. I actually think an amazing thing just happened. I think that as he was talking, he looked at his picture because he had a couple of instances where his face kind of went like this. And then he very, very naturally fixed it. In fact, I have a suspicion that most students wouldn't have caught that, right? That was really, really cool. Because we listened to it again, right? The very first thing that he said was just wrong by a sign. And then he even said, and negative charges go the other way. Then he said this wonderful analogy, right? That water flows down, heat flows from hot to cold. It was a fantastic analogy that basically the positive test charge does all the things that you would naturally think about doing. And then he drew this arrow, and then he said a negative would go the other. It's like totally fixed. So that was really cool, right? Didn't need to redo the video. Didn't really need to call attention to it, because some students would be like, wait a minute, I'm super confused. You just said not to listen to you, and then you said to listen to you. He just kind of motored forward. And if you go back and look at his face, I think wow, that was actually really cool. He either realized it was a mistake and thought the best way to go would be just to say it again correctly, or was wondering if he said it wrong and thought, well, I'll just say it right now. I mean, one of those two things happened, but fundamentally, they both led to this really awesome result. Man, that was really cool.
Moving. So negative charges are going to move from lower potential toward higher, whereas positive charges move from higher to lower. So that's why we're going to probably stick with that general idea. It's kind of a weird concept. Potential, I don't really like it, electric potential, but we use the concept of voltage. Here's another example. Let's say I have a particle that has a certain mass. So this 1.8 times 10 to the minus 5 kilograms and a charge of 3 times 10 to the minus 5 coulombs. It's released from point A and accelerates horizontally until it reaches point B. So this charge starts at point A and it's going to move there. And it says the only force acting on it is an electric force. And the electric potential at A is 25 volts, or 25 volts greater than at C. I don't know what that means. This should be
awesome.
25 volts more than at B. So
that's exactly what I was thinking.
That's a typo on my part. And it says, what is the speed of the particle at point A? Or point B, sorry. Can't speak. So for this one's kind of an interesting one. What we're basically going to end up doing is we're going to use energy conservation. So we've got, at these two different points, we've got kinetic energy and potential energy, but now it's electric.
All right, looking at the time, I think I'll bring this to a close. But man, this is a fantastic example, and you know what a follow-up would be. What happens if this was a negative charge? Well, it would just run the other way. It would never get to B. But you could put the negative charge at B and it would run to A. So I really, really loved what he was doing here. I teach this stuff all the time. And I just sort of get myself ready. I'm like, man, they're going to struggle with this. And so I'm constantly giving them scenarios. Okay, this particle going from here to here, did it want to do that? I'll say things like that. Did it want to do that? They'll say, oh, yeah. It's a positive charge heading towards a negative charge. So I'm like, great. So its potential energy, it went down. That's what it wanted to do. It wants to give up its potential energy. I'm like, great. What about its potential? Oh, hang on a second. Was it a positive charge or was it a negative charge? Oh, it was a positive charge. Oh, then, yep, the potential went down too, right? And so I don't think the math is super scary. The math is actually really straightforward. This is a wonderful little thing to use if you happen to be in the lab and somebody tells you what voltage it's been exposed to. This is super easy to do. Boom, boom, and you're done. So, man, so many cool things about this video. And we're not even halfway through, but I think we'll let it be here. I just think that the analogies were super awesome. The careful attention to the detail in this problem and the other numeric problem, the really awesome critical thinking on his feet to fix the mistake that he made, but then fixed it by sort of editing the drawing. That was super cool. All right, everybody. Well, I hope you have a great day. And remember, physics teachers are awesome.